Okay, dear students, now proceeding to the next question, question number 9. Here we have a certain line integral questions again. If C is the boundary of the region bounded by y is equal to x and y is equal to x squared, then you are asked to find the line integral of this vector function xy plus y squared along I and x squared along j. Basically, dear students, this just recalls the concept of what's called Green's theorem, because considering these two different functions, y is equal to x and y equals to x squared, you are supposed to have a certain bounded region. So whenever you have a sentence that says boundary of the region, you need to recall that concept, Green's theorem concept. So using this Green's theorem concept, we are going to find the line integral of this one. So this is how it can be done. So here it is, using Green's theorem, we do have this one, the line integral of m dx plus n dy is equal to the double integral of nx minus my dA over a certain region. Or so Green's theorem associates line integral with double integral, as can be shown. So what you need to do is you have to identify the I component of your vector here, and the j component of your vector, because the I component is considered as m and the j component is considered as n. Or try to take m to be the one before dx, so this is your m as you see, and the one before dy is considered to be n, so your n is going to be x squared. So since these two make a certain closed and bounded region, the integral of this vector function over this closed bounded region having anti-clockwise or counterclockwise orientation is the same as this double integral of the partial derivative of n with respect to x minus the partial derivative of n with respect to y over what? The enclosed region, okay? This is the idea of this Green's theorem. So your m is, as I said, directly taken from this one. It is xy plus y squared, and from this you are supposed to calculate what my is because it's used here, so we need to find my. So my is a partial derivative of m with respect to y, so it's going to be x plus 2y, and your n is going to be the coefficient of dy, so it is x squared as you see. So the partial derivative of n with respect to x comes to be 2x. Now, even though you are asked to find this question, students, you are indirectly asked to find this one, because basically we can solve this directly as it is, but we need to carry out this integration 2 times. One for this integration and the other for this one. But instead of applying 2 integrations one after the other, we better have this double integral, because solving this double integral is by far simpler compared to this one. That's why I'm doing this. Basically you'll be asked in such a way too, okay? So this is going to be the same as this one. Look, your nx is already obtained 2x and your my is already x plus 2y, so you need to take the difference between the two. So this makes 2x minus x, and this will be minus 2y dA. And this is done over that bounded region. The integration is done over that bounded region R. Look, here it is, students. This is a graph of the parabola y is equal to x squared passing through the origin, being opened up as can be shown. And the line, y equals x is, this line, the linear one passing through the origin. So where can you have now the bounded region? The bounded region is going to be somewhere over here as you see, okay? Since the orientation has to be in an anti-clockwise direction or counterclockwise direction, you need to move from 0 to 1 first, and then from 1 to 0 back, okay? So point of intersections can be obtained. Look, here we do have one point of intersection at the origin and the other is at 1. This basically can be done by solving these two simultaneously. For instance, y and x are the same, so in place of having y here, you may take x here. X equals x squared comes true when x is either 0 or 1, or you can take x you can bring this x squared to the left, x can be taken, then 1 minus x equal to 0 can come. So you do have two options for x to be true. One is either x0 and the other is x to be 1. So based on this you can find point of intersections at 0, 0 and at x1, y1, right? At x1, y1. So this integral is going to be performed over this region, right, students? So this dA is going to be now written as dy times dx, because this is a vertically simple region. As you see, we can just solve that by using vertical simple region approach. So as can be shown here, our dy dx is written here, but when you see the y extension, here we are having what, students? Here we are having the lower function is the parabola x squared. That's why I wrote here EC underneath, and the upper part is EC y is equal to x. That's why I'm having here x upper, and this integration is going to run along the x-axis from 0 to 1, because everything here is this region lies between 0 and 1, so 0 to 1. Now let's find this integration. So clearly this is the integral from 0 to 1, as you see, and when you integrate this respect to y, this comes xy, as you see, and minus 2 y squared over 2 actually can come, but 2 cancelled by 2, then y squared can follow. Evaluation is performed from x squared to x, as you see, so we need to substitute first x in place of y, and then x squared in place of y, and then we will deduct these two. In doing this, what comes next is this one, students. You do have the negative of the x cubed minus x to the power of 4. Sorry, students, you need to avoid this one. It is written here without careful consideration. And anyway, no problem, just avoid these two, x and x squared. So what is the integral of this x cubed minus x to the power of 4? So simple. This will be x to the power of 4 over 4, and should be x to the power of 5 over 5, but you have to evaluate 1 in place of x, and finally negative 1 over 20 is going to be obtained. This is how the line integral of this is obtained. Okay, just associating with the Green's theorem, we can have such kind of solution. Look, had you been doing by the given expression alone, you may just undergo two line integrals, because for this particular integral, for this particular curve, for the lower part you do have one integral, and for the upper part you do have another integral, because finding the line integral over a curve, over the curve C, is finding the two line integrals over C1 and C2. So instead of doing that, we better tackle the problem by using Green's theorem, as you see. I hope you have understood. And what comes next is question number 10. So you are given with a certain velocity field here, students. This is your velocity field, and at any point xyz, the velocity field is given by this expression, as can be shown, and you are asked to find a place where the fluid can be divergence free. So in order to know that, what you need to do is you have to look for the divergence of this v, and the divergence of this v has to be equated with 0, because it is 0 that we can have the case where we don't have either the case where we don't have either sink as well as source. So we have to look for, you see, the place where the divergence of this is going to be 0, because it is 0 that we have divergence free condition. So the solution goes like this. So now look, the divergence of this velocity field is calculated, and it is directly obtained by taking the partial derivative with respect to x of the first component, which actually is x cubed y z squared. The partial derivative with respect to y of the second component, as you see, x squared y squared z squared. The partial derivative with respect to z of this one, as can be shown, x squared y z cubed. So clearly the partial derivative with respect to x is 3x squared y z squared, right? 3x squared y z squared, and the partial derivative of this with respect to y is 2 comes down to x squared y z squared, and the partial derivative of this with respect to z is 3x squared y z squared. So look, all these three terms are, you see, like terms, so we can operate them. 3 plus 2 makes 5, and 5 with 3 makes 8. 8x squared yz squared. So we need to now observe the case where this can be 0, and clearly it can be noted that at a place where x, either x0 or y0 or z0, this goes to 0, right? And we know that at x0 we do have yz plane, and at y0 we do have xz plane, and at z0 we do have xy plane. So whenever you see the fluid is around the planes, you see the velocity field comes divergence free. That is the idea. Okay, students, I hope you have understood this one. So this comes 0 when either x is 0 or y is 0 or z is 0. So whenever the fluid comes around the planes, the case where divergence free is going to happen.